Hi, everyone. Welcome to join the Spark Summit and attend my session. And my name is Binwei Yang. I'm from Intel. And the topic I want to talk today is Apache Arrow-based unified data exchange format between CPU and the accelerators. Firstly, let's introduce myself. I'm 13 years old. I have 13 years experience on the performance analysis. After I joined Intel, I worked on the software optimization in several projects. When I optimized the software, I realized that I needed to know what happens inside of CPU, so I digged more and more into CPU microarchitecture, and eventually, I got an opportunity to start work on the CPU simulator directly. I run the workloads on CPU simulator, find the bottleneck, develop new features to solve it, and I even design the new instructions, implement it on the simulator, hack the compiler to generate the binary, and verify the performance. So give a piece of code, I roughly can know what happens inside of CPU and during the work. One biggest impression to me is that the software doesn't take use all of hardware's potentiality. When I analyze the trace, in many times, the performance can be boosted much if I just use another way to implement the function, or even just change the instruction sequence. And but the solution from hardware is expensive, and especially when sometimes it's unnecessary, because we can solve that from software very easily. And so after I joined in 2018 August, I joined the Spark team and started to lead several projects of Spark optimization. But I'm a layman of Spark Apache Spark till today. I read less than 100 lines of Spark code. I even don't know much about the Scala programmer. And that's why I have some. I stand at the outer side of Spark and have some ideas here. And I don't know how complex it will be, but I think this is the correct direction we should work on. We know that people's pursuit of performance is endless. That's why we released the second generation of Xeon scalable processor. And we have released the Optane DC persistent memory. That's all for the performance. And we also have our FPGA, where we worked on the accelerator of FPGA and many other accelerators. Meanwhile, we worked on the software optimization a lot. We try to enable the software and optimize the software for the new accelerator and optimize the software for CPU. And to boost the performance, one way is to offload the critical functions to accelerators. We all know that. And today, without the offload, this is what happens. Firstly, we have the internal rule format, and we run on the tungsten SQL engine, and then we get the internal rule format after and the output. And when we offload to accelerator like FPGA, we usually do several things here, and it's fortunately that Spark already uses off-heap unsafe-row, so we can take use of it and the off-heap data format. So we don't need to convert the data from on-heap to off-heap. And firstly, we have the internal rule. Then we need to convert it to FPGA bench, and then send the data from CPU memory to FPGA memory. And then we start the FPGA pipeline. We start the FPGA SQL engine, and then FPGA SQL engine generates data on the FPGA memory, and then we copy back the data from FPGA memory to CPU memory, and then we convert it back to the internal rule. This is what we do on FPGA offloading today. And when we talk about the performance boost, we see that one possibility is that the to FPGA and from FPGA take a little time, and the FPGA offload take much time. So this is good. our work is done if we have this data breakdown. But unfortunately, in most of the cases, this is what happens. To FPGA and from FPGA take lots of time. And the FPGA working take very little time. And what happens in our team is that the FPGA, the accelerator team, start a project. They tell everyone that we can optimize, we can boost the performance by 20%. But when we enable it in Spark, we finally get that, we finally tell them that we can only boost by 2 times. And no one is happy on the results. That's why we need to boost the performance again. And when we look at the offload, when we look at the offload, we have several overhead here. Firstly, we need to convert from internal row to the FPGA bench. Secondly, we need to do the data movement. So when we optimize the offloading, we need to start from here. And one way is to use a unified data format between the FPGA and the Spark. So we need, if we use a unified data format in Spark and FPGA, then we don't need the data convert. We can send the data directly to FPGA. FPGA start work it, and get a result, and then copy back to CPU. And one thing we need, when we talk with FPGA team, one thing we need, they are seeking that they are not a Spark expert. They don't need to install Spark on their developer machine and generate the data and debug on their engine. So we need a third party of a unified data format that FPGA can easily debug, generate, and analyze. And secondly, the FPGA team wanted to do is their library can be used, can be shared with many other projects, not only for Spark. So if we use the internal data format of Spark, the other project cannot take use of it directly, and this is what they don't want. And if we optimize the data convert, if we optimize the data transfer, the ideal solution is that we use integrated FPGA. In that way, the FPGA and the CPU share the same memory. We don't need to move the memory between them. That's the ideal case, but actually, we cannot get that. We have to use the FPGA and the PCIe card today, and there will be data movement. But we can solve the problem from other way. That's the double buffer. We are familiar with that. We use 2 buffers. When we copy 1 buffer, the FPGA working on the second buffer. And when FPGA work is done, or the data copy is done, then we switch the buffer and start to work the next column, next way, next buffer. And when we use the double buffer, we have 2 ways. One is use a bunch of rules. The other way is use a bunch of 1 column each time. And when we look at the circles we used here for the demo last year, that we obviously see that there are many columns here, and we can transfer the data for 1 column each time to FPGA. FPGA process 1 column, and then we transfer the second column. Actually, when we look at the FPGA, the accelerators, most of the accelerators, the columnar data format is friendly to them actually. And so this is the pipeline. So when we pipeline the data movement under the SQL engine, we will get either the PCIe or the accelerator be fully used. That will become a bottleneck. And we need to optimize the hardware bottleneck later. But we all talk about the accelerators. Many teams talk about accelerators. But one question is that, do we fully utilize our CPU today? I asked many colleagues in our team, and they said no, we don't use that, and I don't believe. I think that the Spark and the OAP framework and the AVX should be very friendly to rules operations where we can't use. And then I design this simple test. It's a sum of a float. Then I use a proof state to collect the instruction returned, repeated single instruction returned. And you know the answer, it's 0. So it's not, AVX is even not used in Spark today. And I'm surprised on that, and I say that we need to solve that, firstly, before we talk about the accelerator boost performance. And then we need to add AVX support to Spark. What we need is that we have to do research and internally on the AVX support by some other team. We have also tried to do the AVX support under AVX support to have. And when we do that, we know that firstly, we need a columnar data format. And secondly, we need a native LLVM SQL Engine. Because we have tried that on the GVM, and tried to let the GVM generate the similar code, and we found that the quality is not good as the LLVM-based SQL engine. And secondly is that when we have the new instructions for the new CPU, we must wait until the GVM support those instructions. But on the LLVM-based, we can be easier to support the new instructions. So that's why we need to use the LLVM SQL engine, native LLVM SQL engine. And secondly, we need to take use of other highly optimized libraries. Because when we have a team to optimize the various libraries, and if I wanted to use that library and into Spark, they don't need to generate one version for Spark dedicatedly. We need to take use of their work and don't duplicate their effort. So what we need is that firstly, we need a standard columnar data format. It should be easily debugged. It should be easily generated and shared with many teams. And secondly, we need to share with all the projects, not only for the Spark. And the second thing is that we need to implement a series of tungsten backend, not only for the GVM, using the GVM today. Today we only support the GVM, and we need to generate the LLVM native SQL engine, FPGA, and many others, and the tungsten backend. And when we see that Apache Arrow, we said that Apache Arrow is the best choice for this effort. And it's a standard data format, and for native tungsten backend, and it's also for all accelerators, offloading Spark SQL engine. What we want to implement is a plug-and-play tungsten backend. For example, we have several operations here. We can easily take one operation, run on one accelerator, or run on the native LLVM SQL engine, or on others. We need to implement a very flexible tungsten backend and plug in one backend, one operations easily into the tungsten pipeline. And also we need to use, if we use Python UDF, we transfer the data from Spark to Python without any convert. We just send the data directly to Python, and Python do that because we already use the same Arrow format. And we also need to keep all the data on off-heap. We want to move the data in on heap. In that way, we need another convert. And we can do more on that. Currently, the GVM working on the rule format. We can also evaluate that if the GVM can operate on the column data format directly. In that way, we will use the column data format and the unified and the base data format Spark should use. After we support this, after we use the column data format, we can take more use of the Intel Optane DC persistent memory. We can use that. In some cases, we found that there are several operations. They operate on very little columns, 1 or 2 columns, but they need to carry the data from here to there, carry a full table of data. But the other columns is not used, it's not processed, it's just a copy from one position to another position. And in this way, we can put the hot columns on DRAM, but put the other not commonly used column to the persistent DC memory. So the CPU and accelerator can operate on the DRAM memory directly, and when the operation needs to touch the uncommonly used columns, it just read the data from persistent memory to CPU and do some process and convert the data back to and put the results on the DRAM memory. So we can easily use that. The advantage of the persistent memory over disk is that the persistent memory have a higher throughput and much higher IOPS. It also can be much easier to write the program. And it also can be easily ported when we have enough DRAM memory. So if we don't have enough DRAM memory, we put some data on the persistent memory. But if we have enough DRAM memory, we just need to, we don't need to convert, we don't need to modify the program a lot. We just put it on the DRAM. And we also need to use the Optane DC persistent memory when we suffer the data. When we suffer the data, after we get the data, we put the hot columns of data on heap, on off heap, and put it into the DRAM, but put the other uncommonly used memory columns into the Optane DC persistent memory. And we also can offload the Json CSV or Unzip to the storage API. One open source project is called DELS. We are working on that. And we wanted to support the arrow format from the DELS directly. DELS is a unified arrow storage format. And we wanted to support the arrow format from this, from the unified arrow interface. In that way, the DELS can convert the JSON and the CSV or Unzip data and convert it to arrow format and send the data to Spark. And DELS can also offload the JSON and the CSV and unzip the data to the FPGA, to inner FPGA, and it just work on that, get the data format, get the results, and send it to Spark. And it can also use highly optimized libraries to do that. For example, we have the CSV library, and the DELS can take use of it and generate the arrow format of data and send it to Spark. There is no data convert between the DELS and the Spark. This is one thing we are working on. And the other thing we are working on is that we can push down the filter and the project operations to DELS, to the arrow storage API, like the DELS. And it can do on the filter or the project on FPGA. So after we support the arrow format, we use the same unified data format. And actually, we can do the filter and the project inside of Spark, or we can offload, we can push down it to the storage. There is no difference. So it depends on which one is more efficient and which one has a better performance. But on the other side, if the DELS support the filter and the project of push down, it can be shared with other project, and well, it's not only for the Spark. And it's also, we can also connect to other machine learning and AI framework. This is a proposal of JIRA 24579. There is no data format convert between the Spark and the rules framework when we send the data. So after we send the data, how they process the data, it's the format, it's the framework's work. So this is all I'm presenting today. And as you see, it's just a proposal. I didn't show much performance data because we are still working on them. And we are working on several projects today. And firstly, we evaluate if we can use Arrow format as a standard data format inside of Spark, how complex it will be. And secondly, we are working on the native LLVM SQL Engine. We try to enable AVX support in Spark. And thirdly, we are talking about with the accelerator team to see if we can use Apache Arrow data format and unified data format they can support. And they are still working on that. And fourthly, we use our devs. We talked with our devs team to seeking if they can support the Arrow interface. In that way, they can use a highly optimized CSV or JSON path library and generate Arrow data format and input to Spark directly. And so what we need to do is that you share your comments on the Jira 273/96, and it's created by Robert. We didn't create it. And you can also follow our work on the GitHub. It's our team's GitHub. And let's bring the Spark's performance to next level. So I think that's all I'm going to present today. Thank you, everyone. By the way, it's the first time I speak publicly in front of so many people, so I'm somewhat nervous. Hope you get the idea I'm trying to show. Yeah.
Do you have benchmarks for the optimization indeed at different levels? For example, just Arrow format plus JVM, and Arrow format plus LLVM, and Arrow plus FPGA?
No, we are still working on that. The question is that if we use Arrow format and get the performance of the FPGA, LLVM, and the other accelerators, so we don't have the data today, and we are still working on that.
So if you use Arrow for the data exchange between Spark and the FPGA, do you think it's the data copy is still the major overhead, no matter what optimization you do?
Yeah. So when we break down the elapsed time of the FPGA offloading, we see that the data convert is the biggest overhead actually when we offload. I remember the FPGA working time is about 12 milliseconds, but the data copy and the data convert takes about 36 milliseconds.
Hi. Regarding the Arrow in-memory format that you had, are each columnar batches compressed or uncompressed?
It's uncompressed in memory.
Okay, so sorry, when you convert from JSON to individual column batches, do you have a batch size or what? So
I think the batch size should be configurable.
What's the best batch size you have seen?
So actually, we don't have any performance data. We are still working on that, so we don't know what's the inside of these configurations, what's the impact of these configurations. But I believe that it should be configurable over this.
Okay, and you spoke about having a native SQL engine to process this. Do you already have that, or?
Which engine?
You said in order to process the columnar batches, in-memory columnar batches, you wanted to have a native SQL engine. Do you already have the engine, or?
We have worked on the native SQL engine by our team 2 years ago, and we get some performance data. They said that we can get 4 times better performance, but it's 2 years ago. Okay. And currently, we just pick up that project and start to do more analysis and see if we can do more on the native SQL engine. And this is one thing we are working, and we believe that the performance boost should be aggressive, should be very good.
Okay, thank you.
Can you speak to if there's any effort at this point regarding what you're doing to bridge the gap between Spark and FPGAs, and then what the OpenVINO team is doing with inferring on different accelerated hardware? Is there any kind of connectivity there?
Sorry, I didn't catch your
The OpenVINO inference platform that Intel's building, do you know if there's any kind of effort to tie in what you're doing to call Spark and the FPGAs to that use of FPGAs? I assume no.
And I didn't follow the question.
Never mind.
Sorry.
Hey, do you support just FPGAs or any other accelerators as well?
This is for our accelerators. Actually, we take an example on FPGA here, and internally we worked on several internal accelerators as well. And that's the basic idea that we need a unified data format. If it's just a FPGA, we just tell the FPGA team that you give me your internal data format, and I can take use of it. But if I have several accelerators, we need to tell each team that we need to work with each team that we need to convert our data into their data format and get the accelerator integrated in. And so that, sorry.
I don't think it was you.
Yeah. So we are working. That's one reason we propose that we need to use a unified data format between all the accelerators.
And what about GPUs? Do you support GPUs?
No,
No?
currently we are still evaluating on the accelerators. Okay. And I think that the GPU, if the GPU supports other format, we can take use of it as well.
And is any of this available online already on GitHub?
No, I pressed somewhere here. Oh, okay, thank you. Oh, sorry.
I was asking if any of this is available online on GitHub or anywhere else.
No, currently it's still not on GitHub. And after I get some results, I get some in progress, I will put that on the GitHub here.
Is there a timeline?
No, I don't have a timeline here.
Thank you very much.
Okay, any other questions? And thank you all for your attendance today.